Good morning, everyone, and thanks for joining me today to learn the basics of deep learning. This high-level, not too technical introduction to deep learning will help you understand the basics of why deep learning is so powerful and how it works, the challenges many organizations face when getting started with deep learning, and the GPU software, training, and end-to-end family that NVIDIA provides to address these challenges. First, let's start with some definitions. Artificial intelligence is a broad field of study focused on using computers to do things that require human-level intelligence. It's been around since the 1950s, playing games and inspiring scary sci-fi movies, but it was limited in practical applications. Machine learning is an approach to artificial intelligence that uses statistics techniques to construct a model from observed data. It generally relies on human-defined classifiers or feature extractors that can be as simple as linear regression, or slightly more complicated bag of words analysis that made spam filters possible, which was really handy in the late 1980s when lots of emails started showing up in your inbox. Then we invented smartphones, webcams, social media services, and all kinds of sensors that generate huge mountains of big data, and the new challenge of understanding and extracting insights from that data. Deep learning is a machine learning technique that automates feature extraction using large amounts of data to train complex deep neural networks. Deep neural networks are capable of achieving human-level accuracy for many tasks, but require tremendous computational power to train. A few years ago, researchers started applying deep neural networks in a variety of areas and reporting amazing results. It turns out that deep learning is stunningly effective across many domains, and it's transforming the way computers achieve perceptual tasks such as pattern recognition, computer vision, speech recognition, and behavior prediction. Some people, including Bloomberg and the World Economic Forum, have even started referring to it as the fourth industrial revolution. A few examples. Facebook's Deep Face feature creates a 3D model of your face from your online photos, adjusts for lighting and facial expressions, and identifies you in photos with 97% accuracy, all using deep learning. You may have experienced this when Facebook alerts you that a new picture of you has been posted and gives you the option to blur out your image. Microsoft's Skype Translator performs instant translation of conversations in over 40 languages, using deep learning to automatically transform your spoken words into text that can then be analyzed using standard translation methods. Other examples include medical researchers detecting genes associated with autism spectrum disorder, neuroscientists detecting and suppressing the brainwave patterns responsible for epileptic seizures, and using deep learning to identify skin cancers, classify lung sounds, and accelerate computational drug design, saving millions in research. Just imagine a day in the not too distant future when Facebook puts all this together and notifies you that you may have early stage skin cancer, so you can consult with your doctor and get life-saving treatment. Many people want to know why and how deep learning is being adopted so quickly. Well, there were really three key ingredients or initial conditions that made this big bang of modern artificial intelligence possible. First was big data, the huge collections of examples from which computers can learn. Second, researchers needed to develop parallel algorithms that allow data scientists to design and train deep neural networks to process the mountains of big data. And third, was the introduction of GPU accelerators that made it possible to complete massive amounts of computation in a practical amount of time. Early researchers published their algorithms and neural network models in journals, but they also released their software, packaged up in high-level open source frameworks that others could use, so you don't have to start from scratch. And all of the major deep learning frameworks support GPU acceleration because it just wasn't practical to do this computationally intense work without GPU accelerators. Cloud platform providers recognize the potential of deep learning to improve their own services and the business opportunity of offering GPU-accelerated deep learning platforms in the cloud. Now, all of the major cloud service providers make GPUs available to their customers. This significantly reduced the capital costs and time investments for startups, which motivated a huge influx of venture funding for deep learning startups. More than $5 billion in funding is already fueling AI startups, and research firm Tractica is projecting a $500 billion opportunity over the next 10 years. Now, large companies, governments, and other organizations, influenced by the impressive achievements of startups and researchers, are rapidly adopting this new technology, seeing it as a competitive advantage, or, in some cases, a threat if they fail to effectively master it. More than 19,000 organizations have engaged with NVidia to apply deep learning in their work so far. So now that we've seen a few examples of applications that benefit from deep learning, let's explore how deep learning works by comparing it with earlier approaches to machine learning. Consider the traditional approach of performing computer vision tasks, such as image classification or object detection. A domain expert, a human being trained in computer vision, comes up with a set of rules to extract features from the image, such as edges, corners, color information, etc. The expert has to implement these rules by hand, writing software routines, and then figure out how all of the rules should be connected in relation to each other to perform the task. As you can imagine, this can be tedious and error-prone, and if the data changes, then it's back to the drawing board. All of this results in tons of source code to write, debug, and maintain. In contrast, the deep learning approach is to teach the computer the rules for performing the task directly from the data. A data scientist can simply provide a deep neural network with thousands of examples and train it how to perform the task. The advantages of this approach include reduced reliance on domain-specific experts, the ability to extend and adapt to new data simply by retraining the network, and immense performance improvements using NVIDIA's GPU accelerators. As a result, the deep learning approach can be more accurate with significantly less human effort. And it works not only for computer vision tasks, such as image classification, object detection, and image segmentation, but also for non-visual tasks, such as pattern recognition, speech recognition, and behavior prediction. Let's take a look at how deep learning actually works in practice. Here, you can see a very simple model of an untrained neural network. At the top of the model, there is a row or a layer that has 4 input nodes. And at the bottom, there's a layer that has 2 output nodes. Between the input layer and the output layer are a few hidden layers with several nodes each. The white lines here show which nodes in the input layer share their results with nodes in the first hidden layer, and so on all the way down to the output layer. You may hear the nodes referred to as perceptrons or artificial neurons, since their behavior is inspired by the neurons in the human brain. A real deep neural network model would have many additional layers in between the input layer and the output layer, which is why it's called deep. But a simplified model will work fine for this example. Just keep in mind that the design of the neural network model is what makes it suitable for a particular task. For example, the best models for image classification are very different from the best models for speech recognition. And the variations can include the number of layers, the number of nodes in each layer, the algorithms performed in each node, and the connections between the nodes. So if the goal is to train a deep neural network to distinguish between cats and dogs, you would select a neural network model that is designed to be good at image classification. The next step is to assemble a collection of representative examples to be used as a training data set. In this case, several thousand images of both cats and dogs, each with a label indicating whether it belongs to the cat class or the dog class. To ensure the data set is representative of all the pictures of cats and dogs that exist in the world, the data set must include a wide range of species, poses, and environments in which the dogs and cats may be observed. Then, a deep learning framework is used to feed the training data set through the network. For each image that is processed through the network, each node in the output layer reports a number that indicates how confident it is that the image is a dog or a cat. In this case, there are only two options, so the model only needs two nodes in the output layer, one for dogs and one for cats. When these final outputs are sorted, most confident to least confident, the result is called a confidence vector, or sometimes a probability vector. The deep learning framework then looks at the label for the image to determine whether the network chose the correct answer. If it chose correctly, the framework strengthens the weights of the connections that contributed to getting the correct answer, and vice versa, if it chose incorrectly. The framework reduces the weights of the connections that contributed to getting the wrong answer. After processing the entire dataset once, the neural network will generally have enough experience to choose the correct answer a little more than half of the time, so better than a random coin toss, but it will require several additional rounds or training epochs to process the entire training dataset and achieve higher levels of accuracy. It's worth noting that there are readily available models for image classification, object recognition, image segmentation, and several other tasks, but it's often necessary to modify these models to achieve higher levels of accuracy for a particular dataset. So the computation required to train one version of the model is multiplied by the number of model variations that need to be evaluated. All of this processing requires a tremendous amount of computation, much of which can be performed in parallel, which makes deep learning an ideal workload for GPUs to accelerate. There are also many deep learning frameworks to choose from, each with its own strengths, programming language interfaces, etc. But they're all GPU accelerated using cuDNN and other libraries in the NVidia Deep Learning SDK. You can learn more about all of the deep learning frameworks and the NVIDIA Deep Learning SDK on our developer website at developer.nvidia.com. So, now that the model has been trained on a large representative data set, it's very good at distinguishing between cats and dogs. But if you showed it a picture of a raccoon, it would be very confused, since it has no experience with raccoons and would probably report a low confidence number for both dog and cat. If you actually need the ability to classify raccoons as well as dogs and cats, you would simply add a third node to the output layer of the model. Expand your training data set to include thousands of representative images of raccoons, and use the deep learning framework to retrain your network. There's no need to manually write a raccoon classifier algorithm and figure out how to integrate it into your application. Just retrain the deep neural network with your new data set. Once the model's been trained, much of the generalized flexibility that was necessary during the training process is no longer needed. So it's possible to optimize your model for significantly faster runtime performance. Common optimizations include fusing layers to reduce memory and communication overhead, pruning out nodes that do not contribute significantly to the results, and other techniques supported in the NVIDIA TensorRT runtime. A fully trained and optimized model is then ready to be integrated into your application that will feed it new data. In this case, images of dogs and cats that it hasn't seen before. And it will be able to quickly and accurately infer the correct answer based on its training. And your application can be deployed on a GPU-accelerated platform in your data center, in the cloud, on a local workstation, in a robot, a smart camera, or even a self-driving car. There are a few challenges that researchers and organizations face when adopting deep learning. The first is that this is a brand new computing model. Most data scientists, developers, and researchers don't have a lot of experience working with it yet. And to apply deep learning effectively, you need to learn how to approach problems a little differently from a more data-centric perspective. Another challenge is that the algorithms used for deep learning continue to evolve and improve very rapidly. And keeping up with all the latest advances so you can apply them in your work requires significant time and effort. And as you saw earlier, training deep neural networks is tremendously computationally intensive. Until just a few years ago, this made deep learning impossible, or at the very least, an impractical approach for most applications. A final challenge is that once you have a trained neural network, it's really flexible. You could deploy it in a cloud-based web service for low latency facial recognition or e-commerce recommendations. You could deploy it in a powerful workstation for medical imaging diagnoses, a safe and reliable self-driving car, smart cameras for intelligent video analytics, and more. But you need a wide range of GPU-accelerated deployment platforms to benefit from this flexibility. Let's take a look at some of the things NVIDIA is doing to help you overcome these challenges. To address the first challenge and help data scientists and software engineers quickly ramp up on deep learning, the NVIDIA Deep Learning Institute provides hands-on training that gives you the experience you need to solve challenging problems using deep learning. The Deep Learning Institute, or DLI, delivers hands-on training through online courses and online workshops presented by DLI certified instructors. We do this by giving each student a GPU-accelerated deep learning development system in the cloud, so you can learn how to use all the latest open source deep learning frameworks, tools, and more without having to set up your own system. All of the major cloud service providers offer GPU-accelerated systems as part of their platform, so we just use some of them to deliver hands-on training that helps you get started with deep learning. And of course, the training covers not only the image classification workflow that we talked about today, but also application domains such as self-driving cars, healthcare, intelligent video analytics, IoT and robotics, finance, and more. In the last year, we've trained over 10,000 people, and we're scaling up worldwide to meet the increasing demand. One of the best ways to quickly master deep learning is to attend the GPU Technology Conference, or as we call it, GTC. This year, we're hosting GTC the second week in May here in Silicon Valley, and I hope you'll join us. Over 300 of the 500 sessions this year will be focused on AI and deep learning. At the conference, you'll hear from experts across a wide range of industries, as well as academic and government organizations sharing their work on applications in healthcare, automotive, finance, aerospace, defense, retail, manufacturing, and more. You can also be among the first to experience more than 20 brand new hands-on training labs presented by the Deep Learning Institute and leading framework developers, including Caffe2, Chainer, CNTK, MATLAB, MXNet, TensorFlow, and Theano. Key speakers are coming from NVIDIA, of course, as well as Google, Amazon, Microsoft, Walmart, Facebook, IBM Watson, Salesforce, Boeing, Ford, the Chinese powerhouses of Baidu, Alibaba, Tencent, OpenAI, Stanford, MIT, Oxford, University of Toronto, several national labs, and well, I'll stop there, but the list goes on. GTC is really the only place where you can connect one-on-one with so many experts across so many industries. Register today using the code you see on the screen to save 20%, and check out the website for special education, government, and nonprofit rates. NVIDIA also invests heavily in delivering software that you can use to quickly take advantage of deep learning. An example of this is the NVIDIA Digits application, which puts the power of deep learning into the hands of data scientists. Digits simplifies common deep learning workflows for image classification, object detection, and image segmentation, such as managing datasets, designing and training neural networks on multi-GPU systems, monitoring performance in real time with advanced visualizations, and selecting the best performing model for deployment. Digits is completely interactive, so you can focus on designing and training your networks rather than programming and debugging. NVIDIA also works closely with all the major deep learning frameworks to ensure they support the latest GPU-accelerated algorithms available in the NVIDIA Deep Learning SDK. So if you're comfortable with C++ or Python or Java or Lua, all of those programming languages are supported by one or more of these open source deep learning frameworks. And the good news is that all of these deep learning frameworks already have built-in support for GPU acceleration. And for developers who want to build their own deep learning capabilities from the ground up, NVIDIA also provides a comprehensive deep learning SDK that includes all the latest GPU-accelerated deep learning algorithms in the CUDA Deep Neural Network Library, or cuDNN, a complete suite of dense and sparse linear algebra routines, which comprise the low-level building blocks for many deep learning algorithms, the NVIDIA Collective Communications Library, or NCCL, for high-performance multi-GPU performance scaling, and last but not least, the TensorRT Deep Learning Runtime for advanced neural network optimization and low latency runtime performance. NVIDIA also provides a wide range of GPU-accelerated platforms you can use to accelerate deep learning training and inference application workloads. If you want a fully integrated solution, we recommend the DGX-1 supercomputer in a box, which delivers the performance equivalent of 250 CPU-only servers. If you just want to get started on a prototype using your existing workstation, the Titan X Pascal supports fast 32-bit floating point and 8-bit integer performance for deep learning applications. In the data center, the Tesla P100 with NVLink technology delivers strong scaling support for mixed workloads across both high-performance computing applications and deep learning training and inference workloads. And for scale-out inference workloads, the Tesla P4 supports high-efficiency, low-latency performance with fast 32-bit floating point and 8-bit integer support. And of course, if you need to deploy deep learning applications in automotive or embedded robotics type applications, NVIDIA offers the Drive PX and Jetson platforms. So in summary, to address these challenges, NVIDIA delivers training and tools for a new generation of data scientists and developers via practical hands-on training from the Deep Learning Institute and easy-to-use deep learning workflow tools like Digits. The Deep Learning SDK, which is frequently updated with new optimized algorithms and supported by all major open-source deep learning frameworks. High-performance deep neural network training solutions you can use in the cloud, data center, and workstation environments, and a wide range of deployment platforms with software and hardware optimized for deep learning inference in the cloud and data center, as well as automotive and other embedded applications. And so with that, I'd like to thank you for your time and all the great questions you've shared with us via the chat window. It looks like we have a few minutes left, so I'm going to look for some questions that haven't been answered yet and pick a few to answer live. If you haven't already registered for GTC, please visit the website to learn more, and I hope you'll decide to join us for the conference in May.